is Greg Chirikjian from my old institution, from Hopkins. Thanks very much, Greg.
Thanks, Dorothy. So I'm going to switch gears here a little bit, and this is going to be pretty much purely a math talk. And I'll be talking about keeping track of total orientation in DNA, as well as sort of coarse graining the concept of twist. But before I do that, I always like to start by showing where I came from. I didn't come from biology or mathematics. I came from the robotics area, looking at snake-like robots. And I've been told subsequently that this looks a little bit like remodeling in chromatin. I think you can take my word for it that we do things that also look like reptation. And we also built robots. And back 25 years ago when I started my PhD, the idea was this was supposed to capture a Soviet satellite from outer space. There's a little reptation there. So now that we've made the world safe for democracy, I thought I would move on to biology and leave the robotics area a little bit. So in terms of DNA modeling, there are many different kinds of models. The ones I'm most familiar with are those that overlap with the polymer physics literature, the semi-flexible chain models where you have an elastic filament subjected to Brownian motion. But of course, there are many other models. There's John Maddox's group and the BIROD. There are discrete base and discrete base pair models. And then there are models involving averaging over a number of base pairs. You can take many of the people on this list and permutate the names across the different areas because they've all worked on various aspects of these different models. We just had a paper from my group published recently on relating these different models to each other and taking the parameters from one model and putting them in the other models, etc. But the main question for the talk today is how, given a continuum filament that's twisted, if we take discrete reference frames along that filament, how can we keep track of the total twist? And how can we go the opposite direction? Given discrete reference frames, how can you extract twist from that by fitting a smooth curve to it? Classically, the curvature and torsion are the quantities used to describe a space curve. This is not new math. This is a little bit more advanced than polar coordinates, as Eric was mentioning the other day. But it's from 1849, so that's before the American Civil War. This was the mathematics of the day. So given a curve x of s, where s is the arc length and x is the position vector to any point on the curve, one can extract the curvature and the torsion. And these are important because these are intrinsic quantities. You can completely describe the shape of a curve from the curvature and the torsion. And any space curve can be framed. In other words, a reference frame with its origin at a point on the curve, its z-axis along the tangent to the curve, and two other vectors defining the local x and y axes can be defined using the Frenet-Serre apparatus. Now, this is the most common way to frame a curve, and curvature and torsion certainly have their place in the world. For example, the Ferry-Milnor theorem says that if you integrate curvature along a closed curve, then if that closed curve has a knot in it, that integral of curvature must be greater than 4 pi, greater than or equal to 4 pi. There are other slightly more recent results on inequalities like this. So if instead of a curve you had a tube, okay, a knotted torus, and if one integrates, in this case, the mean squared curvature of the surface of that torus, then it has to be greater than 8 pi, greater than or equal to 8 pi, or if one integrates the absolute value of the Gaussian curvature of that knotted torus, it has to be greater than or equal to 16 pi. So these are the results of B.Y. Chen or Langevin and Rosenberg from back in the 70s. This is just to illustrate that the concepts of curvature and torsion have their place. But one part of the Frenet-Serre apparatus that needs to be modified if one wants to look at DNA twist is that the reference frames that evolve according to the Frenet-Serre apparatus have a bias in them in terms of the twist. And that bias goes like the integral of the torsion. And so when I'm talking today about keeping track of global orientation, what I want to do is define the reference frame that twists minimally along a given curve. And then if you have, for instance, a DNA helix that's then twisting around, then the twist is measured relative to that minimally twisting curve. And so this is also not new. Bishop published a paper, there's more than one way to frame a curve, back in the 1970s, and that's essentially what we're building on here. So just to give a picture to it, if the Frenet-Serre apparatus puts a reference frame at the curve with u being the unit tangent, n the normal, and b the binormal, we can twist along that local z-axis and define a new reference frame that has minimal twist, and then all other reference frames can be defined relative to that minimally twisting reference frame. Now, with regard to the idea of global orientation, so what do I mean by that, total orientation? The easiest way to look at this is first to look at the planar case. So in the plane, any rigid body motion can be described by a position given by x and y and an orientation angle theta. Now in the plane, if you concatenate two rigid body motions, that angle of orientation adds. And we normally think of the orientation being associated with the circle, going from 0 to 2 pi or negative pi to pi. But if we have a curve in the plane that executes loops, we may want to go outside of that range from negative pi to pi. So, and it's possible to do in the plane. All you have to do is let your theta go from negative infinity to infinity. And so that, in the plane, there's no issue with keeping track of global orientation. You just let your angle not be restricted to a range of length 2 pi. So we can distinguish between these two sorts of situations. On the left side, we have loops. So the angle theta going from this initial reference frame to the one at the end will be far outside of the range negative pi to pi. But we just keep track of it as a real number. On the right side, we don't need to do that because the orientation at the end, well, the path that was taken to the orientation at the end has no loops. So whereas the reference frames at the end are the same in both cases, the total orientation is different. Now, the reason why we can do that in the plane is because the real line is the universal covering group for the torus group. Or to put it another way, you can sort of divide the real line up by the integers, or the integers multiplied by 2 pi, to create a torus. Or at a more basic level, you can take a line and wrap it around the circle, or you can take a wheel and have it roll along the line. So you have multiple points on the line that correspond to the same point on the circle. And so if we want to keep track of on the real line, in the planar case, if we want to keep track of total orientation, and we have two curve segments that we concatenate, so we take one curve and we've kept track of how many loops that have been executed there, and we keep track of the reference frames at the end, and then we attach to the end of that another curve, then we can develop a rule for how these motions concatenate, not only the rigid body motions, but how the number of loops add as integers, and how the residual orientation adds at the end. And it's quite simple. Actually, I think I should just draw a picture of this. So if we have one curve here, and it terminates here, and there's a rigid body motion, G1, that takes you from here to here, and there's a total number of loops that you're executing, in this case 0, but z would be an integer more generally. We can keep track of these two numbers, and then if I have another reference frame, so a relative motion going from here to here, the total motion going from here to here is g1 times g2. And if this, I'll put a loop in here, if this has a loop, then here it would be equal to the number 1 instead of the number 0, and we would just add sort of the number of loops. So g1 times g2 tells me the total rigid body motion to go here, and z1 plus z2 will tell me the total number of loops. But if over here I had rotated by pi, and then over here this relative motion was another pi, when those add together there would be another term here. So it's not simply adding the integer part, it's adding the integer part plus the residual that results from the relative orientation of the reference frames. And it's done very easily. It's just in this case, in the planar case, we add the angles modulo 2 pi, and we can get the result. And the last part there, the L's, are just the length. If I give you a segment of length 1 and a segment of length 2, and I add them together, I have a segment of length L1 plus L2. So this is actually, that has a semi-group structure to it. Now, what do we do in the spatial case? In the spatial case, we have rigid body motions where R is a 3×3 rotation matrix, X is again a translation vector. We can still do the composition of rigid body motions, but things get more complicated if we try to add the total twist in. And the reason for that is because the universal covering group for the rotation group is SU2, or which you can think of as the 3-sphere, and it's not a Euclidean space. So we cannot we cannot do what we did in the planar case. We cannot just let theta go into a different range. So if we parameterize space curves in the following way, where we have a rotation matrix that depends on arc length, and we have a position along the curve that's the integral of the tangent vector. So the tangent vector can be written as r times E3. That gives us the local tangent to the curve. Then we can compute the twist in the following way. So the angular velocity of an evolving reference frame, it can be taken as r transpose times r dot, or dr ds, and take the vector quantity of that. And that vector, which is omega 1, omega 2, omega 3, we can then look at the omega 3 part, which is the z amount of twist in the local reference frame. So that's the amount of twist, but in fact, we could just add those together, but what we want to do is decouple that from the position and orientation information at those distal frames. And so, the other thing that we can address is in the planar case, it doesn't, the total orientation can be measured very easily, but in the spatial case, it depends on the particular curve that you use to attach the reference frames at the end. But what this computation shows is that it's not very sensitive to that curve. So in other words, if I give you one curve that's attaching two reference frames and I perturb from that curve, then the amount of twist that you get will not be very sensitive to those sorts of small perturbations. So for example, if the word bundle is used quite frequently, both in mathematics to mean one thing and biology to mean something else. So I won't call this a bundle of curves, I'll call it a passel of curves. So we have a number of curves that have the same starting point, the same end point, and they're not executing various loops, or they have basically the same amount of twist as well. And so if you take any of these curves and look at their twist, they're all going to be quite similar. And so what the whole purpose of this talk is to construct an algebraic object which is similar to what I showed you for the planar case in terms of how does the total twist add. And the simplest way, of course, is that you just add the total twists because you have an integral of twist along each of the two concatenated subcurves. But the thing is that the twist has information in it which is contained in the g's as well. So this is redundant. And so how do you remove the redundant information? And that's why we have a minimally twisting set of reference frames from which we can look at a difference. We can use that as a datum. So I think I'll skip some of this detail. So if h of s is the minimally twisting set of reference frames along the curve, and g of s is twisting relative to it, then what we can do is we can back out or simply remove or look at the difference and compute the amount of twist that has occurred. And that's going to be and we can count the integer number of twists, put that in the z's, just as in the planar case, and we can actually throw away the residual amount because we can recompute that from the g's. If you have a curve attaching the base frame to the distal frame, then you can recompute the twist from those reference frames if they're in that same sort of passel of curves. So we can, it's basically like a robotics problem, an inverse kinematics problem. You have two reference frames, one at the base and one at the end. If you can construct a curve that hits the end, you can then compute the minimally twisting curve relative to that, and then look at the difference between that and the twisted reference frame. So I think I'll skip this and just go to the punchline. So the point is that we have a way to take in these three pieces of information: the G1, the reference frame at the end of a piece of curve, the number of, in this case, in the 3D case, we're not looking at the number of loops, but we're looking at the number of times that the reference frame that has its z-axis along the tangent executes a full circle of motions. So that the z here is an integer. The L is the length. When we multiply or concatenate these two structures together, the rigid body motions multiply as rigid body motions. The lengths add as lengths. And the integer number of turns that you get along the concatenated segment is the sum of the integer number of times that it turns in each segment, plus a function that depends on the g's and the l's, which is more, it's kind of complicated, but that's what comes from sort of the robotics, inverse kinematics side of things. So I'll just say that you know what this is and this is sort of actually preliminary work, is a way to extract twist from discrete reference frames, as well as to coarse grain. If you start out with a set of reference frames evolving smoothly along a curve, and you want to sort of sample at discrete points, it's not enough to just sample the reference frames. One has to keep track of the integer number of twists that gave rise to that curve in between the reference frames. So we can go either way. We can start with a curve and coarse grain, or we can start with discrete reference frames and fit a curve that has the correct twist properties to it. And you know, so this is sort of an abstraction away from the DNA problem, but I think you can see, given the relationship between twist and linking number and all of that, that this is a tool that could be used in the context of DNA modeling. So with that, I'll take any questions that there may be. Okay.
So Greg, you've got the new twist. Do you have the new ride as well?
One thing at a time. I haven't for me, twist was the most natural thing because, you know, I work on geometry of space curves, which usually are not writhed in my application. If all goes well with the robot, it's not writhed. But yeah, I mean, if there's interest, you know, if I get encouragement, I'll go try to tackle some writhed problems.
Greg, I think this is potentially useful, but I guess I may have missed something, but what's H1 inverse and H2 inverse? What are those functions?
Right. So, so in the it's hard to draw in the spatial case, but in the planar case, let's say that you have. So let me call this H1, and let me call this one G1. So, well, actually, in the planar case, I can't draw it because. Okay, so let's stay with the spatial case. So H1 is the reference frame that evolves minimally with minimal twist. Okay, so so at the endpoints, it's going to be the same as this guy, but in the middle, this one will be twisting less than this one, and the difference between them is actually the residual twist.
So it's like a smoothing of the curve.
It's like a reduction of. It's like you have the baseline curve, and then you have something spinning around the curve, or you have the curve with something that's as close to being a parallel evolution of reference frames as possible, and that's how you. That's sort of the datum with which you can measure the twist. And so the H inverse G was sort of looking at the difference and how much the G of S was twisting relative to the H of S.
I think in the interest of time, since we have a photograph before lunch, and the photographer is coming in 10 minutes, then we'll go on to we'll thank Greg again.